Good morning, everyone.
Morning.
Hey, sir.
Anybody have any questions before we get started? Got more people coming in.
I think I did actually. One sec.
Okay, good for go.
See if I can find it. Yeah, I don't have it written down, but it was one of the questions from it was one of the questions from the midterm actually. It was you gave you initial the initial conditions for a ball launched at an angle at a speed and find the velocity of the ball when it reaches half of its maximum height. And when I did that, I feel like I went through such a roundabout way to actually answer that question. And it took me a very long time, but I'm pretty sure I did come out with the right answer. But I was just wondering, was there like a trick that I missed or something? Like,
Yeah, if you aren't too careless, there's a quick and easy way. You just gotta, use clear thinking. So when they say at half the height, that means half the potential energy, because potential energy is directly related to height. However, that does not mean half the speed, which is the common mistake people fall into. So what you're doing is kinetic energy is going to be equal to half the potential energy. So in order for you to absorb that factor of 2, you've got to absorb a factor of square root of 2. So basically what you're going to see is that the velocity would be about the square root of 2 under the initial velocity. So in other words, like if the initial velocity was 100, then you take 100 and divide it by square root of 2, which is 1.414. And that should be the velocity at the halfway height. So that's sort of the quick and dirty way.
I'm not sure I follow on that. I mean, like now that you're mentioning the energies, I can imagine maybe doing like potential energy at the point of launch was 0 because it was considered y equals 0. It was being launched from ground height. So you could say potential is 0 and then kinetic is, you could work out at speed because actually I don't think it gave us a weight of the ball.
That's the beauty of it. Let me show
give
you
us a mass. I mean, I guess you can factor it out because it's mgh plus half mv squared is equal to mgh plus half mv squared.
Right.
And yeah, you could remove mass from all 4 of those factors in the equation.
Or should be plus this
one. So you could just do like 0 plus initial kinetic energy is equal to, I mean, I guess you'd still have to find the maximum height, wouldn't you? No, because you could just calculate what the maximum height is going to be based on what the initial kinetic energy. Well, how would you do that? I guess you'd have to work out the vertical motion being the vertical motion separate from the horizontal motion, I suppose. Because the horizontal motion is going to be constant, so you're never going to lose that kinetic energy.
Right. Well, what you got to remember is, like I said, the total potential energy that this thing can have is going to be equal to the total kinetic energy it has initially.
Yeah.
So this could be, Vx squared plus Vy squared square root. That could be what that individual velocity is, right? And then at the top, the kinetic energy at the top, what you're going to have, or excuse me, at the halfway point, what you're going to have is 1/2 mgh, because the h is supposed to be the 1/2 mark. So what's going to happen is, this one will have a x component that's still there, and that doesn't change at all. But this y component is definitely going to be in there. You do have to break the velocities up into x and y components, but what you'll see is on this side, instead of just having this, you'll have plus 1/2 mvx squared. So then you just set in that, you can actually set in equal to h over 2, and that would be it, because the h is, you're defining it as the max height when you set it equal to the total kinetic energy, whether it be this way or this way plus that way. So you see what I'm saying?
Honestly, not really.
Okay.
Maybe we could talk about it after class.
Yeah, it's not a problem, but yeah, that if it's thrown straight up, it's easy peasy, because you're just going to take the, like I said, the 100 divided by the square root of 2, because you've got to account for a 1/2 that's over here inside that initial velocity, and the way you do that is divide v by the square root of 2, and then you'd end up getting 1/2 of 1/2 mv squared. But like you said, when it's a projectile in 2 dimensions, then you have to break it up into 1/2 mvx squared plus 1/2 mvy squared equals 1/2 mvx squared plus 1/2 mvy squared plus mgh, where the vy squared is going to go to 0 at the max height.
Yeah, I think that would be the way that it'd probably make the most sense for me to do, like in my head, because I'm not following the other thing that you're talking about
Gotcha.
very well.
Yeah, when I sort of flippantly told you to divide 100 by square root of 2, I was talking about just straight linear vertical motion, not projectile. The complication arises, like I said, with this vx and vy
Oh,
in the projectile. Yeah, we'll work on it right after class if you want.
gotcha. Okay.
Okay. Anybody else have a question? All right. Well, I wanted to specify something, just point out to you that we talked before about the values. Remember, S is equal to R times theta, which you could really treat as X is equal to R times theta, say, and then you'd say, well, dx dt is actually equal to the velocity, and of course that's equal to R times d theta dt. And then I sort of haphazardly flipped in vector symbols all of a sudden, because I said this is going to be R omega. And then later on, I said something along the lines of V equals R omega. Right. Well, I'm scared to put equals on there, because I don't want you thinking that way. This is a complication here. This omega is what we call a pseudo vector. And basically, we define the direction omega with another right-hand rule. So basically, if you imagine something, say, circular, rotating, let's say rotating this way, then you curl your fingers in the direction it's rotating, your thumb points in the direction of omega. That is the direction this omega is considered. And now you see why I do not want to put v with a vector symbol equal to this side. Right? Just because obviously the direction is not going to be the same as that, because the direction of the velocity is clearly that. Right? So that's sort of the danger of writing that. But I wanted to clarify, this is a pseudo vector. Its direction would be defined as pointing out of the page in that case, pointing into the page in this case. And it's a pseudo vector because it doesn't obey the rules of algebra. So you remember those things that we learned as sort of, well, depending on how you had your high school algebra class, they either used them as rules at the end to tell you that everything was abiding by, like the distributive property, the commutative property, A plus B is equal to B plus A, or A times B plus C is equal to AB plus AC, and A times B is equal to B times A. Those are we're kind of depending again on how you had your algebra class. Some algebra classes took these as rules that you could use to solve equations. Other algebra classes just taught you how to solve equations, and then later taught you these rules and said these are rules that must be obeyed. And you had to memorize the commutative property, the distributive property, the division property, all those weird little things. Well, it turns out those things are actually rules for something called a vector space. And if something obeys those rules, then those things can be considered vectors. This omega doesn't obey those rules, so it's actually what we call a pseudo vector. So omega is a pseudo vector. That's PSEUDOVECTOR, and specifically because it doesn't obey these rules. And the way you can see it, your book does this. If you imagine a mirror, and you have a particle moving with a velocity v, then the image of that particle also has a velocity v pointing to the right. However, if you have a disk rotating this way, okay, you can see by the right hand rule, the omega vector points this way. Okay. However, when you see the mirror image of that, this is represented by an arrow going that way. That means omega should point this way in the reflection. The fact that they're not equal is sufficient to show that that is a pseudo vector, not a vector. Okay, so I just wanted to point that out. There's ways you can deal with it with pseudo vectors, but it's more or less just a convenient way to remind you that, hey, this thing does have directional properties. So you have to consider one direction positive and another, and the opposite direction then becomes by default negative. That's really covered by the rule that I showed you, and this is the way they do it in statics. For instance, you put an X, a Y, and this, and put a plus sign around it. If you just use that and stick to it throughout the whole problem, then you don't have to worry about the idiosyncrasies of it being a pseudo vector and all that stuff, just as long as you stick to the rule that you state. Now, you don't always have to do right up and right hand and counterclockwise. You can do any one you want, but what I'm saying is write one, choose it, and stick with it. Okay. So any questions on that? It'll become a little bit more clear when I work a couple examples for you. All right, well, I've done one pretty good kinematic type rotational motion problem, and I think those are so trivial, I don't want to waste your time doing those. You've got like 3 or 4 in your textbook. What I want to jump to is the idea of torque and some different ways of calculating torque. And then I want to jump to some actual problems, sort of like the Atwood machine. So let's start off with talking about torque. So the definition of torque is actually R cross F. Okay, it is literally a cross product. Now, the way, again, you calculate a cross product is you can take the determinant of a matrix where you put I hat, J hat, and K hat as the first row, and then you put the first vector, R sub X, R sub Y, R sub Z, the first vector's components in the second row, and the second vector's components in the third row. And that will actually give it to you. And there's, neat little rules for that and so on and so forth. So for instance, I showed you about expanding on the minors and stuff like that. So this one is in the slot 1, 1, first row, first column. -1 to the 1 + 1 power is +1. So I'm going to cover up this column and this row, and then take the matrix of these 4 that's left, or take the determinant of this matrix that's left. So for instance, you're going to say R, Y, F, Z minus R, Z, F, Y, I hat. Then I'm going to do the other one, which is, this one's a 1, 2, first row, second, or excuse me, this is a 2, 1, first row, second column. So this one is a negative, and the way I fix the negative is, again, I cover up this row and this column, but I take my determinant backwards, and then that takes care of my negative sign. So I'll say this is RZ FX minus RX FZ, and I'll put a J hat by it. And then finally, the K hat, we're back to a +1. So I'm going to cover up that column and that row, and then just take the regular determinant, which would be RX FY minus RY FX. Notice how once you write the first one, you automatically know what the second one is. You just reverse the subscripts. Not only that, notice that all 3 of them are different: X, Y, Z, Y, X, Z, Y, Z, I, or Y, Z, X. ZYX. So that's another way of keeping it straight. So that's it. Now, what we've learned also, though, is that torque in magnitude would be equal to R times F times the sine of the angle between them if you put them tail to tail. So you could say maybe this is the R vector and this is the F vector and this is the angle theta. When you do that, what you can do is complete the parallelogram, and you realize that one way of looking at it is you take the component of R that is perpendicular, because R sine theta gives you this one. So you take the component of R that's perpendicular to F, and then you just multiply it by F, and that'll give you the area inside. But you can also say, take the component F that's perpendicular to R and multiply it by R. So those are 4 different ways of calculating a torque, at least the magnitude of it. And then remember, the magnitude can be made into a vector just by realizing that the cross product always gives you a vector that's perpendicular to both R and F. So in this case, R cross F would go into the page. R cross F, and then my right thumb's pointing down into the page. So now that we have that, I want to show you a couple of examples. Let's imagine, for instance, a sorority, and they have a really, really big, well, actually, let's take a simpler case first. Okay, let's take just a wrench. So we have a hex nut, which is basically a nut like you work in a building stuff or your car or whatever, right? And we put a wrench on it. Okay, and then we find out it's really, really, really hard to loosen, so we put a breaker bar on it. And like normally the wrench, say, would end like this. With a breaker bar, you put something on it like a sleeve or something like that, because you really want to get a buttload of torque. And then that extends the length, so you can actually extend the lever arm. So let's imagine a scenario in which this distance is in fact 1.00 meters. And then right there, we apply a force F equals 100.0 newtons. And this angle is 36.9 degrees, because evidently you've got to stick your arm in through a hole and reach it there. So you can't really get a nice, ideally perfect perpendicular force to it. So you have to put it at that angle. So you want to calculate the torque. So well, again, we can use torque is equal to R cross F, or we can use torque is equal to R F sine theta, or R perpendicular F, or F perpendicular R. In this case, it looks really convenient to me to use F perpendicular R, and this is the one that I always teach basically in physics. They don't show the other, they don't use this one too much in physics, but it's really comes in handy. That's why I'm going to show you these 2 examples. So this one's pointing, it has a perpendicular component right here that's pointing in the negative, what I'd normally call the negative Y direction. And then it's got a parallel component that's pointing in what I'd normally call the negative X direction. The main thing is to realize that R is the vector that points from the center of rotation to the point of application of the force. So the R vector is in fact this guy. So I could, in principle, take these 2 vectors and put them tail to tail, coordinatize it, calculate this long thing, but that would just be a nightmare and it's stupid. Why would I even do it? Well, it's much easier just get the magnitude and then realize that R cross F really is going into the page. So I've already got the direction, easy peasy. And in fact, I'm not going to waste my time calculating the magnitude by even using the sine of theta. I'm just going to use the component of F that's perpendicular to R. I see that 36.9. I immediately realize that means this 36.9, which is the smaller of the 2 angles, has to be opposite the smaller of the two sides of a 3, 4, 5 triangle. So this one's the 3, this one's the 4, and this one's the 5. And to make that hypotenuse, which is the obvious long one, into 100, I have to multiply it by 20. So that means this one's got to be multiplied by 20, and that means that one's got to be multiplied by 20. So I can immediately tell that the torque, which is equal to F perpendicular times R, is going to be 3 times 20 newtons, which is 60 newtons, times 1.00 meters, and I get 60.0 Newton meters. Again, that's the exact same unit as the joule, but we never call it a joule when we're dealing with torque. We always call it a Newton meter or a foot pound or a pound inch, or excuse me, a pound inch or something like that. So any questions on that one? So notice, just by recognizing this as the component of the force perpendicular to the R and recognizing its role in a 3, 4, 5 triangle, I could immediately do the math and figure out that this length was 60 newtons. Therefore, 60 newtons times 1 meter gave me 60 Newton meters. Nothing on that one? All right. The next problem takes a little bit bigger drawing space than I'm allowing right now. So let's imagine we're wanting to put up a gamma at a sorority house. Real life example here, right? So if you want to put up a gamma, so the Greek letter gamma in uppercase looks like this basically. And I'm not going to do very well at drawing it scale. I will draw off the measurements. And that's pretty much how I'll deal with that. So I'm going to say this distance from here to here is 5.00 meters. I'm going to say this distance from here to here is 2.50 meters. I am going to say that this distance right here is 0.500 meters, and that this distance right here is also 0.500 meters. And of course, that would suggest this one right here is also 0.500 meters. Okay. What I'm going to imagine is that the point of rotation is right there, that corner. So that's basically where you might imagine a axle being. Okay. And what I'm going to do is apply a force F equal to 100.0 newtons right here. Okay. Now that means our R vector is the vector from here to there. And as you might suspect, that's a little bit of a pain in the butt to build, because I'd have to recognize, okay, well, it's going to go over this amount and then plus this amount, and then it's going to go up this amount, which is this plus this, and it'll work. And you can easily coordinatize it, for instance, and make it into a cross product situation. But again, that's a lot more work than really is necessary. You should be able to see that R cross F is going to point out of the page here, and we could just use one of our formulas. In this case, I find it super easy to take torque is equal to R perpendicular times F. In other words, if I can find the component of R that's perpendicular to F, then I'm golden. Well, F is obviously horizontal. That's what I tried to draw here, right? And then you can see that R is this, which is really this vector plus this vectors. This one's perpendicular to it. Notice that's 5.500 meters. high. So really all I got to do is do 5.50. Technically, this other one's not significant. That's the meters times the 100.0 newtons. So I'm basically going to move this decimal 2 places to the right. I'm going to say 550.0 Newton meters. So that's the advantage of making a smart move like R perpendicular times F, as opposed to actually doing the vector. If I wanted to do the vector, I'm going to go ahead and show you that now. Let's say I would immediately write R. I would say this is my coordinate origin right here. So there's my X, there's my Y. Then I'd say R has an X component equal to, okay, that looks like 2.5 from here to here, but that's 0.5 to the left of the origin. So I'm going to say 2.00 meters in the I hat direction. And then up, I'm going to go 5.5 meters in the Y direction. And I'm going to say F is just negative 100.0 newtons I hat. And now I take the determinant of I hat, J hat, K hat. This would be 2.00, 5.500, and 0. This would be negative 100. This would be 0 and 0. If I do the I component, nothing. If I do the J component, nothing. If I do the K component, then I get this, which is nothing, minus this. So I get plus 0.0 Newton meters in the K hat direction. Notice this is automatically built in. I told you in this case, when you put them tail to tail, R cross F would be pointing out of the page. That's why I've been telling you X, Y, Z is a right-handed coordinate system, because it automatically chose out of the page. If you had drawn a left-handed coordinate system, then this would be wrong. So the right-handed coordinate system is definitely a necessity, but still, you see, you get the same answer. It just was a lot more difficult and more of a pain in the butt than when you did it this way. Notice when I did the K, that's a 1, 3. You know, it's the first row, third column. So negative 1 to the 1 plus 3 power is negative 1 to the 4 power. That's even, so that means it's a positive. And then I just do the regular determinant of this 2 by 2, which is this minus this. There's a negative here, and it's already minus, so that made it positive. So that's why that worked out that way. Any questions on that? Pretty straightforward, right? Okay, so now that we have that, what I want to do is show you a couple of rotational motion problems where we're actually doing mechanics. So this will be example 3. Okay, and this one I'm going to assume again a massless pulley, but I'm going to do some things, and then I'm going to substitute some numbers to make sense out of it. So I'm going to call this RA, and then I'm going to have a bigger pulley that it's attached to, and its radius is RB. Okay.
Could you pull the paper down?
Yeah, thank you. Now what I'm going to have is a rope tied to this side, and this will have a big mass. And then I'll have a rope tied to this side, and that'll have a little mass. For right now, I'm going to assume pulley is massless and frictionless. Later on, we'll be able to correct that, or later on we will correct that, or at least I'll show you how. So I'm going to solve this problem like we did before. And I'm going to draw a free body diagram for the left object, which is I have an object of mass big M. I'm going to go on the assumption that its mass is so big that it's going to cause this one to win over the larger radius one. So I'm going to make this into the positive direction. So everything consistent with this big M going down is going to be the positive direction. Now I have acting in the opposite direction is a tension sub L. Okay. Now, according to this mass, what it feels is there's a rope slowing it down from falling at 9.8, and it's calling that tension T sub L. Okay. Now I'm going to draw a free body diagram for little m. And this time it feels a tension T sub R, slowing it down, or in this case, maybe even yanking it up. Notice I made that the positive direction because that's when the right side goes up, that's consistent with the left side going down. And of course, gravity is trying to slow it down with a force of mg. Now I also have a free body diagram for this. Now, if I actually had a mass and a moment of inertia, it'd be a lot easier. But I'm going to draw it out, and then, like I said, I'll correct it in a second. So according to this pulley, this inner pulley feels a tension TL trying to rotate it this way. And that's consistent with this going down. So I'm going to make that a positive direction. But it also feels a tension pulling it this way. And that's T sub R. Okay. So if this pulley was massless, you wouldn't get much out of this equation. You just get basically the fact that these two tensions are not equal because they have different radii. Now, if we assume that they have a mass M, so I'm going to call this M sub P and I. So now I'm no longer assuming it's massless. I was just showing you how you'd set up everything as if it were massless. But right here, we don't have anything representing mass, so we can't make too much use of this. All we can realize is that there's a torque, T sub L, which should be positive, and that's going to be R sub A. I think I said R sub capital A. Yeah, R sub capital A times T sub L. And then there's a torque that should be negative, T sub R. And that's going to be R sub B times T sub R. Okay, that's all we can get from that equation whether it's massless. We just know what those tensions are. Okay. However, now that I've added a mass and a moment of inertia, I can actually make basically 3 Newton's second law equations. So let's make those with our free body diagram as this was intended. So for this guy, again, I call it down positive. So what I'm going to do is I'm going to say I've got mg minus TL is equal to big M times A. Okay. Now, big M times A, that's the acceleration of this object. So I actually am going to have to subscript that L just because this one has a different radius than that one. So if this one makes, for instance, 1 turn, this one's going to make way less than 1 turn. And in fact, this one might make a whole circumference, whereas this one might make, you know, a 1/12 of a circumference or something like that. So until I know how these accelerations are related, I'm going to just call them, label them with different things. So I'll call this equation 1. Up here, I'm going to have TR minus mg is equal to ma on the right. And I'll call that equation 2. And now here's the new one. The new one is the summation of the torques is equal to I times alpha. Okay, that's the equivalent of Newton's second law. That's why I drew all this in red and blue and stuff and green and stuff like that. We're pretending that a counterclockwise rotation is positive. So this one will result in a positive torque and this one will result in a negative torque. So I'm going to say the torque, which I've already indicated, is RA times TL minus RB times TR is equal to I times alpha. Now this one I definitely don't have to subscript, because if this makes a 360-degree turn, notice this one's going to make a 360-degree turn as well. So the alpha is identical for both of those, because it's in, you know, radians per second. So however many seconds it took and how many seconds it took for that change, it's going to take that same number of seconds, and how many seconds it took for that change, the exact same number for that given radian or given degree. So this is equation 3. Okay. Now, how many unknowns do I have? Well, I have, I'm assuming I know M's and R's, right? So I don't know tension. I don't know AL. I don't know tension in the right. I don't know A right. And I don't know alpha. So it seems like I've got 1, 2, 3, 4, 5 unknowns, but I seemingly only have 3 equations. Well, what I do know, though, is that A sub R is equal to R sub B times alpha. And I do know that A sub L is equal to R sub A times alpha. Now, of course, they've got to be related by some sign. For instance, we know that A sub R, we considered that the one on the right to actually be going up that way would be positive, and that's also consistent with alpha being positive. So we might have to work out some issues with that. But right now we have our 5 equations, 5 unknowns. Okay, so let's continue working all this out. What I'm going to do first is I'm going to substitute N for alpha. I'm going to substitute, let's say, A sub R. So let's take 4. Now I want to do the left one. Yeah, let's take 5 and 3. I'm going to put those two together. So 3 is RA times TL minus RB T right times I. Now in place of alpha, I am going to put AL over R. And that's AL over RA. Okay. And that's going to be a new equation I'll call equation 6, say. Now I'm going to do the same thing, only this time with equation 4. And equation 4, I'm going to have, actually, Yeah, equation 4 and equation 3. I'm going to take RA TL minus RB TR, and that's going to be equal to I times AR over RB. And that'll be equation 7. I actually didn't get to work this problem before class. I haven't worked it in probably, or anything like it in probably 4 or 5 months. So I'm trying to figure out the best route as we go. So one thing I can do is I can take 1 and 2 and use them sort of like I did before with the Atwood machine. Remember, with the Atwood machine, we had equal tensions on both sides. And when I subtracted one from the other, the tensions actually disappeared. Well, we can sort of try to do that now, but you see that the tensions aren't going to disappear. So what I'm going to do is I'm going to take equation 1 and add to it equation 2. So equation 1 plus equation 2. Notice I actually put a plus symbol there instead of that and. Okay, so when I add those two, what I'm going to get is mg minus little mg. So I took this term and this term. And then I'll say plus tr minus TL is equal to m a right plus little m a left. Oop, I did that backwards. Thank God I got my pen. Okay, so big M is with A left, little m is with AR. Oh, this is so much fun. Okay, so there's equation 8. And this might not look so helpful to you, but let's see what happens here. So notice I have a TR minus a TL. That's sort of what I have here. If I could just get rid of R's, A's, and the RB's and all that good stuff, right? That would be super, super, super helpful. But in this case, I can't just readily do it. And that's why I'm sort of trying a bunch of different things right now to work stuff out. I can relate AL and AR. For instance, I know that S left is equal to R left. Actually, that'd be RA is what we're calling it, right? Is equal to R sub A times theta left. And I know that S right, and remember, I'm going back to that original S equals R times theta thing that we did from trigonometry. I'm talking about a given arc length. I'm trying to relate the A's to the actual thetas. So if the arc length on the right-hand side is swept out through an angle, then that's going to be RB times theta L, theta R, but theta R and theta L are the same thing. Because this pulley, if it makes one 360-degree rotation, this pulley that's glued to it's also going to make a 360-degree rotation. So you can see that's the case. And now we can just relate and say, okay, well, I know when I took the derivative of that, I got the velocity. And when I took the derivative of that again, I got the acceleration. So I can ultimately say that A sub L is equal to R sub A times alpha. And I know that A sub R is equal to R sub B times alpha. And since alpha is equal to alpha, that means we have a relationship between A sub L and A sub R, namely AL over RA is equal to AR over RB. So I can get AL, sorry, I was writing that outside of your page. Sorry about that. So by setting these thetas equal to, these alphas equal to each other, notice alpha would be equal to AL over RA and AR over RB. So now I can get AL or AR in terms of either one I want. That's what I'm going to do, and that'll help me. So let's say I get rid of AR. So I'm going to say AR is actually equal to RB over RA times AL. And now I can plug that back into here. So this is going to be my equation 9, I guess. So 9 into 8 is going to give me M minus M times G plus TR minus TL is equal to M AL plus M times RB over RA times AL. I can make some simplifications now. I can say that M minus M times G plus TR minus TL is equal to M plus M RB over RA times AL. And now I can get something that's more closely related to RAs and RB, and I can do it again with 7. So in fact, I can say AL is going to be equal to M minus M times G plus TR minus TL, all that over M plus MRB over RA. So that will be equation number 10 that we'll make use of in a second. Almost out of time though, good Lord. Okay, so now that I've got that, I can also now look at my torque equations that I had before, and notice I've got a way to get TR minus TL just by changing the sign of either one of these, and then I can relate them, the AL say to the AR. What we did before was we eliminated AR by adding an AL. So by the symmetry of that, I think the smart thing would be remove this AL by using that equation 9 again. So I'm going to take equation 7 and put it in, or 9 and put it into 7. So putting 9 into 7, I'm going to get RA. You are seeing this right? Nope, you're not. Okay, I'm going to get RA TL minus RB TR equals I over RA. So AR is going to be RB over RA, but I already had an RA there. Excuse me, I already had a RB there. Yeah, I was getting with the AR. Yeah, so I already had an RB there. So I'll put an RB down here as well. And then that'll be times AL. Whoa, 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 whoa. Wrote it in the wrong place. So I had an RB down here already. So I'll put an RB here. And then I replaced, of course, the AR with the AL. So I got an AL here. So you can see that automatically converts this to a RB disappearing. And now I can say, let's divide both sides by, well, actually, hold on a second. Yeah, I was going to try to divide both sides by RA times RB. Let's see what happens with that. What the heck? So multiply this side by RA over RB and this side by RA over RB. And what should happen, of course, is TL over RB minus TR over RA is equal to, now in this case, I'm going to get AL over RA squared RB. So that's not quite as helpful as I'd hoped. But anyways, I can reverse the order of that. I can see that is TR over RB minus TL over RA equals negative AL over RA squared RB. Now with that, I can try to get an RB under here and an RA under here by some trick and then putting it in there. That would be the normal goal. But I think because of this asymmetry between the RA and RB, I'm going to have to solve for one of the TRs, one of the T's, either TR or TL, plug it in there, and then just get from that one unknown the other. But I've got to figure out some way to do that. So what I'll do is I'll finish this up next time because we ran out of time, and I'll be doing that, and I'll be doing integration to calculate the moment of inertia, I equals the integral of r squared dm, and that should finish up chapter 10 for us. So if you have any questions, stick around. Otherwise, like I said, we'll finish this up later. I might even make a video later this afternoon and solve this back from scratch, just to have it clear so y'all can look at the study beforehand, because I've got to, obviously, since I hadn't worked this in a while, I've got to remember my little trick that I pulled before to solve it. Maybe I'll remember it and then I can post it for you. I'll send you an email if I do, or like I said, just subscribe to my YouTube channel and it'll tell you every time I post something. Have a good one, folks.
All right, you too, Professor.
Thank you, you too. So we're back on your question, Gavin.
Okay.
So with a projectile motion problem, it's a little more complicated. But what you have is U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus E loss plus work out, or however many terms we need. But in these cases, we're taking all these things to be zero. Not only that, we're taking the initial potential energy to be zero.
Mm-hmm.
Okay. So what we have is 1/2 mv squared is going to be equal to 1/2 mvx squared plus mg capital H over 2. So that's a way you could solve it. But again, you're definitely going to have to take this initial velocity and the angle theta, break this up into Vx and Vy, and use that to basically fill in that part. And the reason why is, remember, the projectile will go like this.
Well, so this, like what you're looking at right there, that's going to find actually a bit of a strange setup, because you're finding it at half height but without a y component.
Actually, yeah, thank you. You caught that. That's good. Yeah. So in that case, it's actually going to be plus 1/2 mv y final squared. So yeah, that's.
And so that would be, it wouldn't be half of the initial y velocity, right?
So this one's going to stay the same the whole time, but this potential energy is going to be half of the total potential energy it gets at the top, and at the top it's going to be just this plus that. So yeah, I think that might be the square root of 2. Maybe that is the quick and dirty. Let me think about it a little bit. So when we get up to here, basically the total energy is going to be 1/2 mvx squared plus mgh. That's at that point here. When we get up to, that's at h, but when we get up to h over 2, the kinetic energy is going to be 1/2 mvx squared plus mgh over 2 plus 1/2 mvy final squared, which you could also do on this side as well. It doesn't really matter, but that's the total energy it'll have And if I wanted to relate this to,
So
this has
I
got to
guess you
equal
could,
that.
huh?
This has got to equal that. So you can see if you
Yeah,
set,
I was gonna say you can do kind of a system of equations there.
Mhm,
And half mv x squared is going to be a constant because that doesn't change.
right,
So you could eliminate the half mv x squared from both sides of the equation.
right. And basically, yeah, this is the total energy, more or less. This is the total
I
potential
think
energy
you
you have,
would, I think you would need to find, you
the
would need to
H max.
find the h first. Yeah.
We can get, let's see, mg h
Yeah,
over 2
because
is equal to
because
1/2
you
m.
would need to find the h first because at the end of that equation, after you've eliminated horizontal velocity, you still have h as an unknown and vertical velocity as an
Yeah,
unknown.
it looks like you do have to.
So you'd at least have to do a couple of steps. But I did an extremely roundabout way using several kinematic equations, and it took me forever.
Yeah, it looks like, I mean, in the stress
Because
of the
it
test,
just it didn't
that's
occur to me
probably
to
a good thing to
use.
do.
Yeah,
Yeah,
it didn't occur to me to use uh kinetic and
conservation of
potential
energy.
energy. Yeah.
Yeah, that was when they were definitely intending you to use potential energy. But yeah, you can work it out with kinematics. That's the nature of physics. And I think ultimately this would be still a little easier than what you did, but you did the right thing on a test. You figure out a way to do it, and a way that's going to pan out, as opposed to a way that you're not sure would pan out. So it's being a little more conservative, even if it takes more work. That's the way I do a lot of things. A lot of times I just solve a problem. I know a way I can work it, and I know it's going to be a lot of work, but I'd rather do it that way than have it not pan out by doing it the other way. But yeah, this does seem to work ultimately. But yeah, you'd have to get you'd have to actually find out H, I do believe, before you can get that. And of course,
Yeah.
H is just gotten by 1/2 mvx squared or mvy squared set to mgh. So yeah, that could probably get that. But yeah, did they give you the initial projectile velocity and angle, or speed and angle?
Yeah, it was 30 meters a second at an angle of 40 degrees to the horizontal.
30 meters per second at 40 degrees. Okay. So yeah, yeah, so at least you had what you could do. So you could get the Vx, you could get the Vy. That constant was going to stay there. When you set these two equal, you can see there's some pretty straightforward ways of getting that. But yeah, you're going to have to solve for something. It's at least a 3-step problem, even with conservation of energy.
Yeah, I with the kinematics, I think I ended up having to use the quadratic formula 2 or 3 times
Oh no, yeah, that's
to
horrible.
actually get to a point where I had a viable answer.
And it just asks for the velocity at 1/2 the max.
Yeah, it's velocity at half of the maximum
Max.
height that it would reach.
You gotcha. So yeah, I guess that's yeah, you work out v y equals v0y minus gt. That would get you the time at which it reaches a height of 0. You set the v final y equal to 0. That would get you the initial, or the time at which it reached the max height. Then you could use x equals 1/2 at squared plus v0t plus x0 to get the max height. Then you divide that by 2 and do the problem over again. So yeah, that might allow you to avoid the quadratic formula that way. But it'd still be a lot of work. It's probably going to be, like I said, at least 3 or 4 steps, no matter which way you do it.
Yeah. I think I had like run into a wall because I mistakenly I did some algebra wrong the first time that I went through the question, and I came out with an answer that wasn't one of the 5 multiple choice.
Okay.
And I was just like, whatever, and I hit an answer at random that kind of made sense, and moved on, and finished out the other questions. And when I was finished with everything else, I came back to it, take a look at it, did more work, discovered my mistake and worked for another like 10, 15 minutes to finally reach the answer, only to find that the correct, I'm assuming it's correct because I did pretty well in the midterm. I don't remember. I don't think it showed me which ones specifically I got right and wrong, but I think it was the correct answer. But when I came out to my final answer, it was the answer that I had just guessed at,
Okay.
at the beginning. So after spending
made you
like
feel good.
25 minutes or so of working this thing out, I could have just left it there and been fine. I was just like, live
and learn.
yeah, I mean, yeah, got through it eventually.
That's cool. Tyler or Vincent, y'all have any questions? All right. Well, do you have anything else, Gavin?
You said you were going to try and like rework through that question with the linked pulleys kind of, or the two concentric pulleys. Yeah, that'd be really helpful. Whenever you're going to upload that, I'll take a look for that because I got lost halfway through that and just could not rejoin you.
It's a really good problem, but I decided at the last minute just before class started to solve that one instead of the other one, which is it doesn't seem that much simpler, but it is a lot simpler because you end up instead of having 5 unknowns, you only had 4. So that makes a big difference. But yeah, I'll certainly see about doing that. That's something I usually just do like right after class on Mondays. I'll sit there with my notepad and my dog on my lap and work physics problems. So I should be able to do that and get a nice clean answer. It's a good, interesting problem. Just you always got to remember there's now another F equals MA, but it's torque equals IA. And once you get that set up, you're good to go usually.
Yeah.
Right.
Wait, I forget. Is our A for torque? Is that kind of like the squiggly A, the Greek A, or whatever?
Yeah, it's the alpha. Yeah, I should have said summation of the torques equals I times alpha, not A.
Gotcha.
But what happens is you almost always substitute something times MR squared for I. And then the A is something the alpha is A over some R. So that's why I mistakenly threw the A in there because it almost always turns to an A on that equation. But yeah, like you see, you'll see when I work it out, it'll make a little better sense to you.
Okay.
Okay.
And then I had one more question that let me see if I can find this.
Go for it.
I found a PDF of, here it is. I found a PDF of the formulas from our physics book, and I was wondering if
yeah, share it.
Yeah, here, I'll share it to you. One sec. It's disabled currently.
Oh. Oh, there you're sharing screen. Sorry about that. I thought you were going to send a text or a chat or something.
Oh, I just want to throw it up. It's it has all of our formulas, and I think there was like maybe 1 or 2 somewhere in here that I wasn't able to find in the book, but maybe it was because I just missed over it. But like if you look at these are all formulas from our book that we use, to my knowledge.
These are perfect. Yeah, these are good.
Yeah, I was just wondering, like, if I grab formulas from here, like if like these look like they're good.
Yeah, you can use exactly that. I have no problem with any of that.
Gotcha. Okay. I can also send you, this was I think this was just a URL. I could send that to you if you wanted to share that with the rest of the class.
I'll share it with the whole class. Like, yeah, that'd be great. Does it have the other chapters too?
Yeah, it goes on. It's the whole book.
Good deal. Yeah, that's excellent. I'd love to have that. Thank you, sir.
Yep, no problem. All right, thank you for your help, and I'll check out that video later.
Okay, have a good one.
You too, sir.
Bye-bye. Tyler, do you have anything, buddy? All right, I don't think he's there. I'm going to go ahead and see about working this problem that Gavin asked about. So if I work out, try to find out what the X component is. This is V0X, this is V0Y. Obviously, I can see that V0Y is equal to 30 meters per second times the sine of 30 degrees. And of course, you see that the sine of 30 would be up here is a 30, so this would be 1/2. So this should be 15 meters per second. And then V0X would be 30 meters per second times the cosine of 30 degrees. And of course, cosine of 30 is √3/2. So that's 30 times square root of 3/2, which is like 0.866. And that's meters per second. I'm going to do 30 times 25.98. So this is roughly 25.98 meters per second, which I'll keep that. This one's 15.00. Really, I should only be using to the nearest whole number. So I'm really going to underline these digits. So I know those initial velocities. If I wanted to do it kinematically, I would just say, okay, V equals V0 plus AT gives me that 0 is equal to the Y component, which would be 15 meters per second, minus 9.80 meters per second every second, times T. And that would give me the T at which it reached max. So T would equal 15 divided by 9.8. And that gives me 1.5306 seconds. There's a lot of extra digits there. That's the time at max. So that means H max is just equal to 1/2 AT squared plus V0T plus X0. But I'm saying initially the height was 0. The initial velocity I do have. So I'm going to say H max is equal to 1/2 negative 9.80 meters per second every second times 1.5306 squared plus, again, the Y component of velocity be 15.0 meters per second times 1.503 or 5306 seconds. So I'm going to get 0.5 times, I'm going to get negative 0.5 times 9.8 times that time squared, plus I'm going to say 15 times, again, that time, and I get 11.47, 11.480. And that should just be meters, 480 meters. Okay, again, a lot more sig figs than necessary. Just carrying a bunch of them. I'm going to do one rounding at the end and call it a day. Now that gives me the H max. What I want to know now is how long till it gets to half of that. Well, that way I could actually use let's say V squared is equal to V0 squared plus 2AX minus X0. I could use that because I know that height. This one's 0. I know that acceleration. I know this. But what I don't want to know is this final velocity. And that would actually allow me to find that final velocity, but that's just the final velocity in the Y direction. So we'll do that. We'll say V at H/2. So V at H/2 is equal to the square root V0Y squared plus 2 times negative 9.80 times, now instead of 11.480, I'm going to say that over 2. And this will be just the Y component, so I got to keep that in mind. So this is going to be the square root of 15 meters per second squared minus 19.6. Actually, no, this 2 and this 2 will cancel out. So actually, I'll just do minus 9.8 times that gives me 112.5 meters squared per second squared. So I'm going to say 15 squared minus that that gives me 112. In other words, that's half as big, which I should have known because I knew what the square of 15 is. So when I take the square root of all that, I get 10.6. So that's just the y component. So what I should find is that the velocity at h over 2 should be 10.606 meters per second squared plus the horizontal component, which is 25.98. Meters per second squared square root. So I'm going to say square that number plus 25 point. Find that number up here, 25.98 squared. And then I'm going to take the square root of that. That becomes the square root of 787.50 meters squared per second squared. And I got 28.06 meters per second. So the velocity at h over 2 should be about 28 meters per second. I'm not sure if that's the answer that he had on the problem he tried, but that's the answer I get doing it kinematically. And actually, I didn't have to do too much because I was wise in choosing which kinematic equation to use so that I could avoid doing quadratic formula. That's part of the reason we do the derivations of where this equation came from. We realized that we had to do some awful squaring by substituting this t, solving this for t and substituting it into here for here. So with that, whenever you feel like you got to do a quadratic formula, it's often better to try to use this because it'll, as long as you can figure out the direction of the velocity yourself, then you're golden. So hopefully that's it.